Okay, uh, I was going to begin by saying that I was wrong about something in the Q&A last week, but I think not everyone who was involved is here, so maybe I'll wait and see if Jacob comes later, and I'll say it then. If not, I'll still say it, but I won't say it until the Q&A starts. So, picking up where we left off last week. So remember, I introduced the gauge argument as it's been discussed in physics textbooks for many years, but also in the philosophical literature now for many years, and then described sort of what I take to be the standard criticisms of the argument, drawing mostly on a paper by Chris Martin, although others have raised very similar critiques. So I now want to begin the process of what I think of as a positive reconstruction of the gauge argument that recovers many of the same conclusions and does so using many of the same kinds of moves. The emphases are a bit different. The description of how the moves work is a bit different. But I think that it sort of is substantially the same and shows something that I think has been overlooked. Now, before getting into that, I want to pause a little and describe a version of a very famous and influential argument that I'm calling the Weierl-Stein argument, though of course many others have made versions of this, concerning the relationship between the Newtonian mechanics, Newton's law of universal gravitation, and classical space-time structures. Now, the idea is that, I said this at the beginning of the talk last week, but just to remind everyone, the idea here is that I want to argue that the gauge argument looks much more like this argument, which I think philosophers have generally been very receptive to, than it is usually observed. So, so recall this is an argument concerning classical space-time. I know everyone's familiar with it, so I won't dwell on it too long, but the particular way in which I'm reconstructing it here matters. So I just want to register the moves. Anachronistically, of course, Newton begins by supposing that he needs a certain kind of structure to express the laws of motion. This is a structure that we now call Newtonian space-time. It consists of a smooth four-dimensional manifold, a temporal metric, a spatial metric, which is required to be orthogonal to that temporal metric, a covariant derivative operator relative to which both of the metrics are constant, and a unit time-like vector field, a vector field whose that when contracted with the temporal metric yields 1 and whose derivative is 0. Now, that unit time-like vector field is supposed to represent what Newton called absolute space. It provides the structure needed to associate points in space at different times. And this is what gives us a universal standard of rest. But we now know his laws of motion require less structure than that. They require only the structure that we now call Galilean, or sometimes Neo-Newtonian space-time. So this is Newtonian space-time without the unit time-like vector field that gave us the structure of absolute space. There are many ways to see this. One is just by inspection of the laws. We see that, in fact, the vector field Xi doesn't enter into the laws, but all of these other structures do. You might think that's not entirely satisfactory, because it could be that that structure Xi was somehow uniquely definable given the rest of it. But we can see that, in fact, no, it's not, by observing that maps that preserve the rest of this, i.e. diffeomorphisms from M to itself that preserve T, H, and the derivative operator, map solutions to solutions, even if psi does not preserve the unitime-like vector field C. Now, there's a straightforward sense in which Galilean spacetime may be said to have less structure than Newtonian spacetime. Again, we can see this in a few different ways, one of which is, again, by inspection. When we've defined Newtonian spacetime, we've written down 5 objects. When we've defined Galilean spacetime, we've written down 4 objects. That gives us a nice sense of there being less associated with Galilean spacetime. Again, there's the question about unique definability, but we can also observe that the symmetry group of Newtonian spacetime is a proper subgroup of that of Galilean spacetime, i.e. Galilean spacetime has more symmetries, or in other words, it's the maps that preserve all of the structure of Galilean spacetime do not necessarily preserve all of the structure of Newtonian spacetime. So we then conclude Newtonian physics presupposes no more than Galilean spacetime, and not the full Newtonian spacetime structure, as Newton, again anachronistically, supposed. Okay. Now you could ask the further question: are we done? Could we posit even less structure? Now, in fact, at the moment, this is a somewhat controversial question. Simon Saunders and Eleanor Knox have given somewhat different arguments to the effect that we could extend this argument and arrive at something that is even weaker than Galilean spacetime. But I think it's uncontroversial that there's a point beyond which you certainly can't go. And so let's consider whether or not a weaker structure of Leibnizian spacetime would suffice for the laws. And of course, this is historically the case that people have been most interested in because of influential arguments by Leibniz that one should require still less structure. Okay, so suppose now that we consider diffeomorphisms that preserved only the temporal and spatial metrics, but don't necessarily preserve a derivative operator. Now, this map will not generally take solutions to solutions. So for instance, if I have for some derivative operator or other that f equals ma, this is just a way of writing f equals ma in this notation, it does not follow that if I push the force along this map, that it'll be equal to m times the push forward along this map of the curve, the acceleration of the curve, according to the original derivative operator. I really should have pushed m forward as well. Nonetheless, I can do something here. Because I can always express the action of one derivative operator in terms of another derivative operator and a smooth tensor field CABC, if I have one of these Leibnizian transformations, I can always find some smooth field such that if f equals ma, according to the derivative operator I've started with, then f equals ma minus this term that depends on the acceleration of the curve after the push forward and the C field. And so there's a kind of correction I can perform such that a revised version of the law will always hold. And once again, I really should have pushed m forward here too. Okay, why is this? Well, it's just a basic fact about derivatives. Covariant derivatives on manifolds, that any derivative operator may be expressed as a pair. So in particular, the push forward of this derivative operator, nabla, is going to be equal to that same derivative operator with this connecting field that allows me to express this action. Now, one way of capturing the idea that Newton's laws really do seem to require the derivative operator or at least part of the structure that's encoded by the derivative operator, is that for this class of transformations, CABC may be non-zero. It's not right. So one way of saying what's going on here is that we really need to keep track of the information encoded by this derivative operator. And if we don't keep track of this particular derivative operator, the laws of motion are not necessarily going to hold under the transformations. Okay, so with that way of thinking about what was going on in the Weil-Stein argument in mind, let's go back to the gauge argument. So recall last week, we started with a free Lagrangian. This was a Lagrangian describing a complex scalar field. Now we can ask, what structure have we presupposed in writing this Lagrangian? This is the same sort of question that we begin with when we're running the Weil-Stein argument. Well, we have a space-time manifold. We have a metric on that manifold because we're raising and lowering space-time indices here in the Lagrangian. We've chosen some copy of the complex numbers because all of these fields are complex valued fields, and we're interpreting them as smooth maps from the manifold M to the complex numbers. We have an inner product on C. Why do we have an inner product on C? I mean, it's sort of hiding in plain sight. It's the standard it's the standard inner product on C. But we need it in order to take products here. So for instance, when we talk about phi squared. And we have a derivative operator acting on these complex valued fields that's compatible with this inner product. By compatible here, I mean that it preserves lengths according to the inner product. So I want to highlight the role played by two things here. First, a fixed copy of the complex numbers, and a derivative operator compatible with this inner product on C. So thus far, we've taken complex scalar fields to be analogous to real scalar fields, right? They're just maps into a particular space. But I can reconceive of any map from M to C as a map from M to M cross C. This is sort of like the reconception associated with the evaluation map. Now, rewriting in this way is suggestive because M cross C, or M times C, the product manifold, is, or immediately gives rise to, a trivial vector bundle over M with a fixed global trivialization. And from this perspective, what we've previously been thinking of as a map from M to C is actually a section of that bundle. Now, just recall in the background here is that a vector bundle is a smooth assignment to each point of M of a copy of some fixed vector space. Now, in the present context, that's our one-dimensional complex vector space, such that the whole manifold is locally diffeomorphic to the product manifold, M times V. And a section is a smooth map from M, which is called the base space, to the total space, E. And a vector bundle is trivial if it is globally diffeomorphic to M cross V, and a global trivialization is a diffeomorphism that realizes that relationship. Now, in general, global trivializations won't be unique. If E is diffeomorphic to M cross V, it will be so in many different ways. And so when we talk of M cross V as a trivial bundle with a fixed global trivialization, what we're doing is we're saying, well, this is the sort of thing, the sort of structure that's should be understood to be invariant under all maps that preserve this pi, this projection map, but which I can choose a particular trivialization, a particular map, and conceive of E as being a product manifold relative to that map. Okay, and so here once again is just to reiterate what was on the last slide. M cross C over M is a trivial vector bundle with the identity as a global trivialization. Now, a derivative operator on a vector bundle is the sort of thing that gives us a notion of differentiation. Now, I should just say, because I think the bundle language is maybe a bit less familiar, but everyone is going to be familiar with sort of the stuff that we use in general relativity. We can think of tangent fields on a manifold as forming a vector bundle. So this is just a generalization of the idea of what's known as the tangent bundle. Ordinary derivative operators on a manifold are linear connections or covariant derivative operators on the tangent bundle. And so here we're just saying, well, there are other kinds of vector bundles we can define, and they also have a notion of differentiation. We can define non-uniquely covariant derivative operators on them as well. And what they're going to do is they're going to give us a notion of differentiation for sections. And so just as there are many derivative operators on a smooth manifold, there are many derivative operators available on a general vector bundle. But any global trivialization uniquely determines one. And one way of seeing that is that a global trivialization gives us a standard of constancy, because a global trivialization, i.e. a map a diffeomorphism that shows us how E can be conceived of as a product bundle, allows me to say, when I'm talking about the same point of V, or in our case, the same point of the complex numbers, at different points of the manifold. This was how when we initially introduced complex fields as mapped from M into C, we didn't have to talk about the derivative operator. We got it for free because we had a standard of constancy that arose from the fact that we knew when a point in the complex numbers was the same. Okay, and so this is just to sort of bring these 2 points together. There are many global trivializations. There are many derivative operators. In general, different global trivializations give rise to different derivative operators. Okay, so let's go back now to the special case that we were considering. Focusing now just on this particular bundle that we've used in defining our Lagrangian, we're first going to note, as I said before, the metric that we're talking about here is the canonical Hermitian inner product on each fiber, right? It's just the thing that takes pairs of complex numbers to this quantity. And we're going to suppose that all of the maps, including any global trivialization, just preserve this inner product. There are certain ways in which this inner product is distinguished, and so we're going to suppose that that's fixed. And this is going to imply that the derivative operators determined by global trivializations also preserve the inner product. So all the derivative operators that we're considering here are also going to preserve lengths according to this Hermitian inner product. So with this kind of background in mind, let's reconsider this question that we started with. What structure have we presupposed in writing this Lagrangian? Now, in the first instance, I'm just going to give the same list using this new terminology. So now, instead of a fixed copy of C, we have a trivial C bundle we have an inner product on the fibers, and we have a fixed global trivialization, which of course we've just said gives rise to a derivative operator. Now, this is the structure we've presupposed in writing down the Lagrangian. But following the logic of the Weierl-Stein argument, we may now ask, is all of this structure necessary to express this Lagrangian? So in particular, we could ask the question, is this Lagrangian invariant under transformations that do not preserve all of this? So in particular, we're going to ask, and the answer is yes. In particular, we're going to ask, are there transformations that don't preserve our fixed global trivialization, but which do preserve the Lagrangian? As I say, the answer is yes. So the first thing to say is that this global trivialization enters in here only insofar as it determines a derivative operator. This suggests that perhaps this Lagrangian should be invariant under transformations that preserve that derivative operator and the metric, but don't necessarily preserve the global trivialization. That is, which somehow map the fibers of this fiber bundle, the vector spaces, into one another in a way that preserves the standard of constancy that we're working with, but where it will give us some different map from our total space E to the product manifold. Now, maps of this form do exist. They're maps that we can think of as implementing a rigid rotation through some fixed angle in the complex plane. So we've got our manifold M. We have this local structure that allows us to associate with each point of M a copy of the vector space C. And what we're going to do is we're going to find some angle, and we're going to rotate our vector space through that angle uniformly at every point of the manifold. When I say uniformly, what do I mean? Well, I mean uniformly with respect to this derivative operator, delta. Right? So I've got from the structure I already have a way of comparing these sorts of transformations from point to point. And now the ones that this derivative operator says are constant transformations over the entire manifold, constant rotations over the entire manifold, are precisely the ones that are going to preserve this derivative operator. Okay, and so maps of this form preserve the derivative operator, but not the global trivialization. Now, you might recognize maps of this form as ones we discussed last week. Maps of this form act on sections by taking the section to e to the I lambda times itself, right? Because again, we're performing a rotation in the complex plane. These are what we've previously called global gauge transformations. Lambda here, of course, is constant. Now, we've already seen that this Lagrangian is invariant under these maps. That was the first step in the gauge argument as we presented it previously, was just observing that this Lagrangian had a certain class of symmetries. Recall, these were the symmetries that gave rise to the Noether charge associated with electromagnetism in this context. Now, again, following the logic of the Weierl-Stein argument, observing that our dynamics are invariant under a class of transformations that don't preserve all of the structure that we thought we needed when we first wrote down the Lagrangian, is a signal that in fact we're using less structure, and that we can move to something weaker, to a new kind of a new mathematical context where we're presupposing less structure. And now, of course, you can ask, well, what do you mean by less structure? But I mean the same thing that I meant before. the automorphisms of this structure, M, eta, a total space or a bundle, a metric, and a derivative operator, the automorphisms of this are a proper subgroup. I'm sorry, the automorphisms of this, the thing with the global trivialization, is a proper subgroup of the automorphisms of this other structure. That gives us a sense in which the thing with just the derivative operator has less structure than the thing with the global trivialization. Another way of thinking about it is that the global trivialization determines the derivative operator, but there are many global trivializations associated with any such derivative operator. Okay, so this is basically the point in the Weil-Stein argument where we say we don't need Newtonian space-time anymore. We can move to Galilean space-time. But now we can ask the further question. Could we get away with less structure? So consider transformations between global trivializations that do not necessarily preserve this derivative operator, but do preserve the inner product. Now, these would be transformations that go from our total space to our total space, implement rigid rotations at each point, but through arrows that, through angles that may vary smoothly as you move over the base space M. So this is not the fully general class of transformations you can consider. This is what I'm proposing is something analogous in this argument to the Leibnizian transformations. It's something where we now try to see if we can give up yet more structure by asking whether or not we can give up the derivative operator by considering specifically non-constant rigid rotations. Now, these are going to be transformations that are similar in some ways to the ones that we considered before. Again, they're going to act on sections by taking us to a rotated value at each point. But we're allowing this lambda to vary over M. Now, of course, we've seen these maps before as well. These are what we previously called local gauge transformations. And so we asked previously, is this Lagrangian invariant under local gauge transformations? We observed that it was not, but we observed that by modifying it, we could again make it invariant under such transformations. So how does that look from this perspective? Well, since these maps don't preserve the derivative operator, they don't in general preserve the Lagrangian either. And this is similar in some ways to what was going on with Leibnizian transformations in the Weil-Stein argument. And so we can conclude from this, just as we could in that context, that the structure that's not preserved here by these maps, by virtue of which the Lagrangian is not left invariant, really is, in some sense, essential for expressing this Lagrangian. Nonetheless, I could ask, could I handle this in the same way that I did Leibnizian transformations in the Weil-Stein argument? Is there some way that I could push this derivative operator forward to ask how the derivative operator would have to change in order to recover the claim that the Lagrangian was invariant? In other words, what further structure do I need to be sure that I've preserved in order to preserve the dynamics? Of course, I can do this. The same kinds of facts about derivative operators apply here as do in the pseudo-Riemannian case. The details are slightly different, but not for any deep reason. What's going on here is that, once again, there's always a connecting field, a field by which I can express the action of one derivative operator in terms of another. In this context, that kind of field is a vector field instead of a tensor field. Strictly speaking, it's an endomorphism valued one form, and so really there are three indices on this object A, but two of them, because we're just acting on a one-dimensional complex space, are just complex numbers. And so we suppress them. That's why this is a rank 1 tensor and the other thing was a rank 1, 2 tensor. Okay, but so there exists such a field such that, so given any two derivative operators, there exists such a field, which is such that given any section sigma, the action of one of the derivative operators on that section is equal to the action of the other one plus this correction term that involves this vector field A. Now, this field A is analogous to the CADC fields, as I've already observed. It holds generally for any pair of derivative operators. I think there's a such that missing here. But so in particular, if I start with a derivative operator on my bundle, and I have one of these local gauge transformations, there's always going to exist some field A with the property that I can express the push forward of my derivative operator along that transformation using this combination of the original derivative operator and that vector field A. But now, in fact, we can observe that for the special case of local gauge transformations that we've already considered, that A field is going to take a special form. So if psi is a map that acts on sections by doing this kind of local rotation, psi is going to act on derivative operators by taking them to that particular derivative operator related to the original one by minus the exterior derivative of lambda, of this now varying measure of the angles of rotation. Now, as we've already observed, of course, if I do apply this transformation to my Lagrangian, right? So I transform phi in this way, and I transform derivative operators in this way. I find that the Lagrangian is in fact unchanged, right? That's exactly the upshot of the claim that we previously made, which was that if we want to impose local gauge invariance, we need to change not just the sections, not just the fields phi in this way, but we also need to change the derivatives in this particular way. We need to transform them by adding a term plus I dA lambda. Okay. Now, going back to the Weil-Stein argument, right? This is exactly the point where we concluded, following our observations about the behavior of Newton's laws under Leibnizian transformations, that in fact, that inertial structure, that derivative operator, which gave us a notion of straight lines through space and time, was necessary for the expression of Newton's laws, or at least that some part of the structure encoded by it was necessary for the expression of Newton's laws, right? That we couldn't get rid of the derivative operator altogether. Now, I want to suggest that we've gotten to a point now where the same observation is warranted. The requirement that in order to preserve the dynamics of this scalar field under transformations of this sort, that we need to transform the derivative operator in such a way that we express that we need to transform the derivative operator. We need to push forward the derivative operator along the map so that all of the relative relationships are preserved, is a signal that in fact we need a derivative operator in order to express these laws, that this Lagrangian presupposes the structure of a linear connection on the vector bundle. So in other words, what we're seeing here is that we don't need more than just this derivative operator. Just like we didn't need the structure of absolute space, we don't need the structure of the global trivialization. Nonetheless, we can't get away with getting rid of the derivative operator altogether, because otherwise the maps that don't preserve the derivative operator also don't preserve the dynamics. And so we use this reasoning to find a kind of intermediate place where it seems that the derivative operator is really a necessary part of the structure in order to express the laws. Now, this is a way of re-expressing the claim previously made in the context of the gauge argument that by imposing local gauge invariance, i.e. by figuring out what we need to do to this Lagrangian in order for it to be left unchanged by these local transformations, we've discovered a particular field. We've discovered a new field, which must, we argue, exist as a part of nature and interact with these complex scalar fields in a particular way. What have we, how have we done that? Well, what we've seen is that this derivative operator, which is expressed using this field A, is necessary to express the dynamics of the field phi itself. So that's like saying in the context of the Weierstein argument that we've discovered a new field, i.e. the field that determines, the derivative operator, which determines the inertial structure of space-time. Okay, so that's the first step of the gauge argument. The first step of the gauge argument is as I presented it previously, was the discovery of this field A and its interaction with matter. In this context, the first step of the gauge argument is the discovery via the symmetry arguments that we don't presuppose a global trivialization, but we do presuppose a derivative operator to express the dynamics of a complex scalar field. Now, recall the second step of the gauge argument in the original formulation was to then say, well, there ought to be some sort of kinetic term for that field A. In the present context, one way of thinking about that question is, well, where does this derivative operator come from? If we're going to attribute this sort of structure to the world, we might ask, is there something in the world that in turn determines the derivative operator? Now, I don't claim that this follows via the Weierstein argument, but I do claim that a similar kind of, or not a similar kind of reasoning, but a sympathetic kind of reasoning is going to help. So first, there's something fully novel here. We have to add a new assumption at this point. Now, I think that this is something that maybe in the presentation of the gauge argument that I discussed earlier, people aren't as explicit about it as they could be, but I think that we should be explicit about this. At this point, we need to make an assumption. We need to assume that this derivative operator appearing in the Lagrangian is a dynamical quantity whose dynamics in turn depends on the configuration of phi, the section. Now, we could think of this as an ensemble inspired by general relativity. There we have a derivative operator. There we determine that that derivative operator is dynamically determined via Einstein's equation. Another way of thinking about this is if we wanted to go back to the Weierstein argument and run a version of Eleanor Knox's argument about that leads via similar reasoning to Newton-Cartan theory, we could do so. We could make an argument something like, well, perhaps that derivative operator in the Weierstein argument in Galilean space-time is itself determined dynamically in some way. And we can ask, how that happens. But in any case, for our purposes right now, it's fine to just say, well, what if it's determined dynamically? What sorts of dynamics are allowed? In other words, what sorts of dynamics are compatible with the structure that we've just argued is the structure presupposed by the Klein-Gordon Lagrangian, the Lagrangian for this complex scalar field. And the answer is a result due to Uriyama in the 1960s, analogous in some ways to Lovelock's theorem in general relativity, which says that the only first-order Lagrangians on the space of derivative operators on a vector bundle that preserve no further structure than the structure we've already attributed to this bundle are polynomials of the curvature of the derivative operator. Now, that curvature is, you can think of it as this exterior derivative if you like. It's curvature in a sense strongly analogous to curvature in a pseudo-Riemannian manifold. It's going to be a 2 form, which is equal to the exterior derivative of A. Now, the only such polynomial that is both non-vanishing and at most quadratic is this FAB squared term. Now, this is, of course, the same term that we added at the end of the gauge argument, the kinetic term for our new field A. Previously, we argued that it was, in running the gauge argument, we argued that it was perhaps the simplest such term or something like that. Now we have something a little bit more concrete to say, which is that it's the only quadratic non-vanishing term that is compatible with the structure that we've arrived at through this kind of symmetry reasoning about the Lagrangian. Okay, so just to wrap things up, let's return to the 3 critiques of the gauge argument that we discussed previously, following Chris Martin. So the first one was that standard justifications for the move from global to local gauge invariance are unwarranted. But now I think that the perspective that I've offered here really changes the situation. So we aren't moving from global to local gauge invariance exactly. What we're doing is we're using a study of the symmetry properties of these dynamics to investigate how much structure or what structure is necessary to express this Lagrangian. Local gauge invariance, as implemented in this argument, is automatic. We're just pushing something forward. And we're observing that if you have some relationship between tensor fields and you have some smooth invertible map and you push everything forward along that map, the same relationship is going to hold mutatis mutandis. What's going on in this argument isn't that we're imposing some new invariance. We're asking what structures do we need to push forward in order to achieve that invariance, right? We already know that if we push everything forward, we're going to get invariance. But we also know that in some cases, we don't need to push everything forward. And if we don't push everything forward, those are things that aren't necessary for preserving the Lagrangian. Okay, and so we're seeing these questions about local and global gauge invariance in a slightly different light. But what we do see is that by asking how these transformations act on this Lagrangian, we get to pick out which structure we want to say is necessary, or to use the terminology that we used in discussing the original gauge argument, what the real fields are going to be. 2, local gauge invariance does not uniquely dictate the form of the Lagrangian. There are other gauge invariant terms one could add. And there's a sense in which that's true insofar as we could use higher order polynomials if we liked, or we could consider the possibility of higher order Lagrangians. But in fact, Uriyama's lemma and the vector bundle structure constrain these terms. And so if we want to restrict attention to first order Lagrangians, for instance, it's only higher order curvature polynomials that are compatible with this geometry. Now, of course, we could consider further terms that presupposed other structure or more structure. there's nothing that prevents us from coming up with new theoretical postulates. But once we have this sort of geometrical picture, there's something very natural, I think, about asking what sorts of dynamics are compatible just with that geometry. And what we end up with is precisely what we ended up with in the original gauge argument. Now, finally, there was the objection that we don't derive the field FAB, but we put it in by hand. Now, there's a sense in which that's true, because we have to add the physical assumption that this derivative operator is determined dynamically by extremizing some Lagrangian. That's correct. That's what the, there is this sort of extra assumption. I would add, though, that once we're sort of clear on just what was needed to express the Lagrangian to begin with, that we need this derivative operator, we're forced to account for where that comes from, or what determines that structure, or how we know what it is. And this is the idea that it's determined dynamically is something that has sort of a long and successful track record in other physical theories, perhaps most notably general relativity. And so I think it's a motivated physical ansatz, even if it's not something that's derived, but rather posited. Okay, that's it.
Great stuff, James. Thanks.
So I had said at the beginning that I was going to say something to Jacob, but he came in just a couple of minutes after that. So Jacob, something that I said in the question period, I went and looked into it, and I was completely wrong what I said about swampland and monopoles. So what's true is that swampland conjectures seem to put constraints on the mass of a monopole. So they have to be very high mass.
Yes, that's correct.
But doesn't rule them out. I still think that what I said about monopoles and the geometric interpretation of Yang-Mills is right. If you really do want to think of this as a connection, globally defined and everything, because wherever there's a monopole, you don't have the connection defined.
You'll have to remind me what your, I don't remember exactly what we said about monopoles last time, except that if they were present, then we would, but what was
so what I was saying was that I thought that they were, I think it's an interesting case, and I think that this is something that I want to think about some more. But it seems to me as if they're kind of a wedge issue for the geometrical interpretation of Yang-Mills theory. If monopoles exist, then at least where they exist, you can't interpret Yang-Mills fields as connections on a bundle, because they break the closure of the curvature.
Yes, that's right. And so you have to sort of work around them. Like if you put a point-like magnetic monopole in the middle of space-time, then and this is actually part of the arguments that lead to electric charge quantization. You end up having to use essentially different charts, overlapping charts, in order to describe what's going on with the gauge field, and the transition functions from one chart to the other. If you regard those transition functions as being related to phase rotations of charged matter, and you require that they have appropriate periodicity conditions, that leads to charge quantization.
So, but I would actually say that argument is, so it seems to me that monopoles mean a few different things. So here's one thing you might mean by monopole. We modify Maxwell's equations. Instead of having just a charge current density in the normal inhomogeneous equation, we make both equations inhomogeneous, and we have a J field and we have a K field, and the K field represents magnetic monopoles. I think that just completely breaks the geometric interpretation of electromagnetism.
Yeah. Yeah, if your monopoles are distributed throughout space-time in not at localized places where you have singularities, but they're just sort of like spread everywhere, then yes, yeah.
But the localized version, I think you can think of as a topological claim. You don't even have to think of this as matter exactly. You can think of this as something about the global topology of the bundle, right? So with the Dirac argument, one way of thinking about it is the role of the magnetic monopole is sort of analogous to the role of the solenoid in the Aharonov-Bohm effect. And so you can think of this you can think of this as changing the topology of the bundle, as opposed to as introducing a matter field that there's no point at which the FAB is defined and FAB fails to be closed, sort of removing the point at the end of the, so.
The relationship of the solenoid becomes formalized if we take the limit as the solenoid becomes infinitely thin, and then it's just a Dirac string.
Yeah, right, which is exactly what Dirac's argument was.
Exactly.
Yeah.
All right, so we have Eric has a hand, Jacob has a hand, and Harvey has a hand. So let's start with Eric. I think you were first.
Thanks, Jim. Thanks, Jim. That was a really rich talk, and there's a lot to ask. We'll talk about, but I'll try to. Well, I'll start with this and see where we go, and maybe I'll jump back in the queue with more questions after that. So I'm curious maybe I apologize for missing the first talk last week. So I'm curious. Maybe you mentioned it there. Why are in the gauge argument are we focusing on Lagrangian preserving maps in the first place rather than solution preserving maps?
Yeah.
What? So, and I mean, in Lagrangian mechanics in general, you can it's generally the case that formally quite different Lagrangians can still give us the same solution vector fields. I think that this is related. A closely related issue is why it is that you argue that the reason why it's natural to consider a local gauge, to move from global to local gauge transformations, is because what we're doing is investigating what structures are necessary to formulate the physics in the first place. Well, again, that move seems to be justified on the demand that what you're looking for is invariance of the Lagrangian, not invariance of the solutions. Mm-hmm. So I'll stop there.
Yeah, so I'm doing what I'm doing here because I'm recovering the moves of another argument that one sees quite often. You could ask, well, why don't we ask about preserving solutions in the gauge argument as it's presented elsewhere instead of preserving the Lagrangian? And I mean, I think of course you could ask that other question as well. It would be a bit like asking the question about Galilean space-time that Simon Saunders asks, right? Because Simon's presentation of Newtonian mechanics gives up on the standard expressions of the laws, but he claims that we can recover the classes of solutions. I don't think he puts it in exactly those terms, but I think that's substantially what's going on, where we no longer have F equals ma because we don't have, A isn't something that we've defined. We don't have the structure to talk about acceleration, but we can talk about we can write down a set of equations that make use only of the structure of Maxwell space-time that preserve, in a sense that needs to be made more precise, the solutions of Newtonian gravitation. And so, I mean, you could ask, well, maybe that's the next step in this argument. You say, well, could we characterize the class of transformations that preserve the solutions to the Klein-Gordon equation? On the other hand, though, I don't think that it's going to make any difference here, because it's not, for instance, as if you apply a local gauge transformation, you get something like a global divergence term or something like that, that we would have sort of good reason to think isn't going to affect the class of solutions to the Euler-Lagrange equations associated with this Lagrangian. But I think at least in the first instance, the question has traditionally been what structure is needed to express the dynamics. And then there's a further question of whether or not there are other expressions available of that dynamics that give rise to the same solutions.
In the Weil-Stein argument, several of the moves that you described can be justified or motivated by the idea of what's empirically accessible to us. That's one of the reasons why it seems cool to give up the standard of rest. Is there anything analogous here about that motivates any of these moves by invoking something like empirical accessibility?
Well, I don't know how many complex scalar fields you've encountered in life.
5.
more than most people, I'd say. No, I mean, look, there's some sense in which this is a toy example, right? Even if you can make it a little bit more realistic by considering spinor fields. I mean, that introduces just a little bit more complication. The argument still goes through in the same way. But even there, we're talking about classical spinor fields, classical Dirac fields, and the physical significance of these things are tenuous. So I think it's difficult to run arguments that are quite as tangible as the versions of the arguments in the Weil-Stein argument, or the versions in the Leibniz-Clark correspondence on which some of these ideas are based. That said, the Aharonov-Bohm effect is sort of a way of making clear the sense in which there really is this derivative operator, not just its curvature, but this derivative operator is empirically accessible. And if you don't have enough structure to say what the derivative operator is, you aren't going to be able to talk about parallel transport around the solenoid. So I think that's the closest we're going to get to. You need at least that much. Right, and in some sense, that's the classical argument, right? You say, well, we don't even need the derivative operator. We just need this field F that we could interpret as its curvature or not. Followed by, oh no, in fact, in quantum mechanics, there are these phenomena that you can only make sense of if you have the derivative operator, not just its curvature. And that looks a little bit like, Leibniz in the role of the FAB absolutist, and Clark saying, no, but what if you have this bucket?
That's really helpful. Thank you.
All right, Jacob.
Thanks. Just lowering my hand. Thanks. That was a really wonderful talk. I really enjoyed it. So I guess I'm a little bit confused at the end though, because well, I guess I'm trying to understand. Why these arguments don't attach to global phase symmetries of the standard model that are not gauged, right? The standard model has, for example, baryon number conservation, which is associated with another global phase rotation, and we don't gauge that. So something is not connecting with me, and I can't exactly put my finger on it. At the end of your talk, you suggested that we've recast this story in a manner that is reminiscent of other historically successful approaches. Mm-hmm. And therefore maybe this doesn't make it a compelling argument, but it somehow motivates it. But I still think that at the end of the day, we're making physical posits that we've just rephrased, but that don't make the local version of the gauge argument really any more physically compelling than they were before. Maybe I can see this in a different way. phrasing everything in terms of fiber bundles is elegant and elucidating. On the other hand, there is a very pedestrian way of viewing what we've done here. One argument is, and this is maybe the more naive, old argument is, look, we have a global rotation, global phase rotation symmetry. It's an actual symmetry of this theory. It's not a local symmetry, but we can make it a local symmetry if we introduce this additional gauge field. And now it's a local symmetry. Maybe there wasn't a good motivation for making it a local symmetry, but we can't. And then we can do it if we introduce this gauge field. And this gauge field, wouldn't it be nice if we're dynamical? I mean, we put it in already. We shouldn't just treat it like a formal thing. We should treat it dynamically. We should find kinetic terms for it. And the symmetries dictate. I think you mentioned that there's the simplest kinetic terms to write down, but for a long time, I think it's been understood that this is really the only thing you can write down that has the right symmetries if you want to keep to the right number of derivatives. So this is the argument that has historically been presented. And what you seem to be saying is, well, we don't have to actually make a posit to make a global symmetry a local symmetry. We can always phrase things in such a way that it's a local symmetry by changing what we're assuming are the fundamental geometric structures that are at play. But there is actually a very pedestrian way to see that as well, which is, okay, we're not going to propose that we're changing the physics by making the global symmetry a local symmetry. We're just going to do a field redefinition. If I take my phi field, my complex phi field, and I simply redefine it to be phi times e to the I lambda of x, this is a redefinition of my field. I'm always allowed to do this. And then if I simply write down what the Lagrangian looks like, it will look different in terms of this field redefinition. I will see these new terms show up. And then I simply notice, look, this thing has a gauge redundancy. If I do a local phase rotation of phi, and at the same time I do a linear shift of lambda to compensate, well, then the theory has a local gauge invariance. This is, I think, just a sort of, like I said, a pedestrian, you're implicitly invoking fiber bundles, but you're not doing it explicitly. And this argument actually has a very long provenance, right? It goes, this is the Stuckelberg trick, where you can do a redefinition of your fields, and you can make a gauge invariance show up for free. To me, the physics is still positing, well, although we've redefined our field in this way, I'm now going to call this redefined piece of my original field, I'm going to call it a fundamental new physical field and give it dynamics and give it kinetic terms. And to me, that's always been the heart of the leap. Why do we do that? We don't do it because we could do the same exact argument up until that point for the global phase rotations that are not gauged in the standard model. For me, the real non-trivial leap is declaring that this is going to be a physical new field that has to have its own dynamics. And I guess what I'm just not seeing in this argument is why that's any more compelling than it was before. Mm-hmm. So I apologize, that was a bit of a long-winded thing, but I think I'm still missing something.
Well, there are a bunch of different things here to try to think about. One is that, what you're describing as the field redefinition interpretation. Another way of thinking about it is that we can reinterpret all of these transformations in terms of coordinate changes, right? And so we could think, and really what we're doing then is we're saying, well, we have this derivative operator, we have this field, let's change our coordinates. How does the derivative operator change in new coordinates? How does the field change in new coordinates? And of course, everything's going to end up being the same. I would still think of that, the fact that we need to change the derivative operator when we change coordinates is a signal that really the derivative operator is necessary here for the expression of the dynamics. So now so I think there are sort of, from my point of view, two big things in what you're asking. One is, what's actually gained from this way of thinking? And the other is, why don't we do this for other other symmetries of the Lagrangian, of the standard model? Okay, so for the first, what I would say is, I think that there are two things that are changed in thinking this way. One is that it no longer looks like we're putting this field A in by hand. What we're doing is we're recognizing that there's something that's playing a particular role in the Lagrangian. Something that maybe the geometrical significance of which we hadn't understood before. Now, I mean, it's always the case that we can write down fields and we can transform fields, but when we redefine our fields, it may or may not be the case that they continue to have the geometrical interpretation that they had before. And so I think that pointing out that this has a certain geometrical interpretation and this is what it does under these transformations to preserve that geometrical interpretation is insightful. Is it more than that? Maybe not, but I mean, it really depends on how insightful you found other arguments that had a similar kind of character, where you say, oh no, there's this geometrical structure that we're attributing to space-time, and it's the properties of that geometrical structure that are probed in this Leibniz-Clark type debate. Now, I agree though that there's this further question of, is this dynamically determined? And that is just put in by hand, if you like, or motivated by other kinds of arguments. But that doesn't change. It's not like we're forced to do that. As for the standard model case, I think that this is really interesting. People do ask this kind of question. Why don't we gauge more symmetries in the standard model? I don't know that I yet have an answer to that. I do think that there's an interesting way of getting at that question, is to ask, well, from this point of view, does it mean that there is structure that the standard model is taking for granted that doesn't seem to be necessary, or something like that? I mean, do we have in the background some fixed global trivialization? On the other hand, though, I mean, you mentioned, for instance, global baryon number, which is a real number, and real valued vector fields, or real valued vector bundles, just behave very, very differently from complex valued vector fields. You can't rotate in the real line. And so it may just be, I mean, for the same reason that we don't need a derivative operator to take derivatives of scalar fields. There's a sort of a unique way to do that. But I'm not sure. I mean, I don't have off the top of my head all of the ungauged symmetries of the standard model. So I'm not sure if that kind of reasoning applies in all the cases.
Maybe I can just clarify. So the way that I understand this approach is, rather than starting with original Lagrangian with a global phase rotation symmetry, and in one single step positing that there is now a physical change, there's now local symmetry, and positing that we need this gauge field all in one go, we've softened the soil. We've rewritten the story before making any physical posits. We've rewritten the story in a way that has softened the soil. It now looks more local-ish, and we can see where this gauge field would have to go, right? Mm-hmm. That's kind of what it seems like is happening here. But we've just sort of shifted the moment we have to make the posit a little bit farther along in the argument. But there's still a physical posit that needs to be made. I guess that's
yeah. So what I would disagree with in that is that we have to take derivatives one way or the other. And now we're asking, these local gauge transformations are transformations that are acting on this bundle, whether we say they're acting on the bundle or not. And now we can ask, well, what happens to this derivative operator under those transformations? So I don't think of us as introducing a field A. I think of us as reifying a derivative operator.
Yeah, I'm in agreement with that. Yeah. But I still, that reification step to me is still sort of the crux of it. What I would argue when I teach, QFT, is just we introduce scalar fields to do certain things. We introduce spin 1 fields to do certain things. And when you introduce a massless spin 1 field, you have to give it gauge invariance for internal consistency. And there are spin 1 gauge fields that do certain things, and there are other places we don't have spin 1 gauge fields. This is why we have gauge invariances in certain situations, and we don't have gauge invariances in other situations. Why do we have to treat the A field like some bizarre other kind of a thing, rather than just treat it like one more kind of field that we introduce? We introduce Dirac fields, we introduce scalar fields, we introduce spin 1 fields. To me, trying to get the spin 1 field to emerge out of spin 0 or spin half fields has always seemed like, it kind of reminds me of canonical quantization, right? I mean, it's a trick, it works, it gives you a theory in most cases that seems to work pretty well, but fundamentally the world is quantum mechanical. Quantization it wouldn't go from classical physics to quantum physics. Fundamentally, there is a spin 1 field or there isn't. And although we can use tricks like this to guess what the structure of those spin 1 fields should have to look like when they're not a fundamental physical motivation for why they have to be there. But I still not quite sure how this changes that, but I completely agree that this picture is very elucidating.
Okay, James, did you want to comment on that, or?
No, I mean, I think we've both said
okay
our pieces.
All right, let's have Harvey and then Neil, and then back to Eric.
Jim, thank you very much. But I want to push you a little bit harder in the direction of Jacob's questions. So I want to ask 2 questions. The first one is basically a minor point of clarification, and the second a little bit more substantive. And the first question is this. Neither in what Jacob called the pedestrian approach to the gauge argument, nor in in your bundle approach, even before you get to the point where you say the field must be dynamical and there must be a kinetic term in the Lagrangian, presumably there is an assumption that the A field, or the derivative operator, is not pure gauge. So am I right in thinking that in your ansatz, even before you introduce the kinetic term, you have to assume that the A field is not pure gauge? And that, of course, doesn't follow, it seems to me, from any of the arguments that you've put forward in the bundle approach any more than it follows from the pedestrian approach. So that's the first question.
What do you mean by pure gauge?
Well, the introduction of a derivative operator, covariant derivative operator, that gives you the symmetries that you desire, the local symmetry that you desire. There's nothing in the argument that says that the curvature associated with that derivative operator is non-zero. So is that very assumption that it's non-zero, I take it as part of the ansatz?
But there are many flat derivative operators.
That's true, but if you have a flat derivative operator, you're not going to be motivated to have a kinetic term in the Lagrangian, which does not work.
That's right. So the question is, why this flat derivative operator rather than other flat derivative operators?
No, but it's not a flat derivative operator. That's
no, I understand. I understand. The motivation, though, is to say, why have we had to choose one flat derivative operator as opposed to any other flat derivative operator? And now we say, well, okay, let's think about our other physical theories in which we've now had to observe that we were choosing a flat derivative operator. I mean, this is happening in the 1960s. We've got general relativity. We've got Newton-Cartan theory already. You might say, well, look, in other cases where we've realized that there was some flat derivative operator that had to be chosen apparently by fiat, that in fact, there's been a sort of underlying physics describing that derivative operator. And it's turned out that it's been possible for it to be curved, and moreover, it's dynamically dependent. So yes, I suppose that at that point where you say this is going to be dynamically dependent, you're also supposing it doesn't need to be flat any longer.
Right.
What I took to be the key move before we got to that was the observation that there really was a particular flat derivative operator. Now, which is the sort of thing that, maybe you wouldn't agree with this characterization, but it's the sort of thing that I think in the first part of, is analogous to the sorts of things that you would say in the first part of dynamical relativity about conspiracies, right? So why this flat derivative operator as opposed to any other flat derivative operator? What's determining this sort of inertial structure? And then, you can run similar sorts of arguments.
Well, let me go to the second question that I had, which I think is more substantive, which is this. I mean, I see a sort of a disanalogy between applying the Weierstein argument to Leibnizian space-time and then making the connection with Newtonian space-time, and what you're doing with complex fields in space-time and so on. Would you say that if you apply the Weierstein argument to Leibnizian space-time, that in some sense you provided a justification or a derivation of the inertial structure in Newtonian space-time?
So what you've shown is that the laws, at least as expressed, presuppose that structure. So in the background is a particular kind of argument that I think Stein attributes to Newton, but which is then propagated since then, that the way in which we discover what the structure of space and time is by trying to discover what the laws of nature are, and then asking this isn't something that you do in sequence, right? I mean, this is something you need to be asking this question as you're trying to understand what the laws are. But you ask, what do we need to presuppose about the structure of space and time in order to make sense of these laws? And the idea of the old story, of course, is Newton thought that in order to make sense of acceleration, he needed absolute velocity. But now we know that he didn't need that, but he did need something. And the idea here is something similar is going on. You think in order to make sense of the derivative of a complex scalar field, you need this global trivialization. But in fact, we discovered through the gauge argument that you don't need that, but you do need something. And what you need is the structure of this linear connection.
Yes, but I quite agree with that. But the question is the application of the Weierstein argument to Leibnizian spacetime in some sense predicting or justifying the existence of the inertial structure in Newton? I mean, it's all very well to say that given Newton's theory, this is what we have to have in terms of space-time structure. But that's not a derivation of Newtonian mechanics. That's simply an explication.
Yeah, that's right.
You're providing more than an explication of the gauge of the gauge fields. You're providing some kind of justification for them on the basis of a Weierstein argument. And I'm wondering, if it doesn't apply in the case of Leibniz, why does it apply in the case of the gauge field? Or maybe it does apply in the case of Leibniz, and so you would argue that, in a parallel fashion, you would argue that you've provided a justification of the inertial structure in Newtonian mechanics.
So, I think that in the case of Newtonian mechanics, there are really sort of two separate moves going on here. So I think that you're entirely right. Once you have the laws, what we're doing here is investigating the properties of the laws and using this principle that the symmetries of the space-time should match the symmetries of the laws or something like that to try to interpret what the space-time structure is.
Right.
On the other hand, there's this, the classic rejoinder to Leibniz is if you think we need less structure, come up with a dynamics that's empirically adequate and uses only that lesser structure. And so there is an empirical argument here that has to do with the empirical success of Newton's laws and the fact that it appears to be very difficult to make sense of a successful dynamical theory that posits less, right? I mean, it took from 1718 until roughly 1985 for Julian Barber to come along. I mean, so there's okay, so, but I think that it's that empirical argument along with, you know, the success of Newton's laws that gives some justification for the inertial structure. This argument by itself doesn't do that, right? Because it could well be that there was another theory that was just as good as Newton's theory that didn't posit all of this. And I think that something similar is going on with the gauge argument as I'm trying to reconstruct it. So all I've done here is start with some dynamics. Dynamics, in fact, that don't seem to characterize, you know, describe any real physical system, right? I mean, there aren't any complex scalar fields, you know, certainly at the classical level. But then try to run this explication. And what I'm trying to do is show that the moves of the heavily criticized gauge argument look a lot like the moves of this explication and have this end result that looks like we've discovered that, in fact, we have presupposed this structure no more and can't do with less in order to express the dynamics in this particular way. Now, there would have to be a further argument that, moreover, we have empirical considerations that tell us that we need laws that have this character. You know, and that's where my answer to Eric would come back, and I'd say, well, you know, we would at that point invoke things like the Aharonov-Bohm effect as an argument that really there is something that looks a lot like this kind of parallel transport structure that distinguishes between different flat derivative operators and is empirically significant. But I don't think that the argument as I've given it in this talk provides some justification, as you put it. I think explication is right.
Thank you.
And so what I'm suggesting, maybe just to finish that thought, what I'm suggesting is that the right way of thinking about the original gauge argument before the ansatz is as explication. It's often presented as justification, and I'm
Okay, Neil.
Hey, thanks, Jim. That was great. So my question was, in fact, the same as Harvey's first question. So, like, at what point is it? Because yeah, I couldn't sort of quite see it in the argument when we were letting the derivative operator have a non-trivial curvature.
Mm-hmm.
But I think, yeah, I found what you said there helpful. And so maybe just an observation of a connection that seems potentially interesting to me is that what you're identifying as your step one, where we sort of recognize that what's really doing the work is a derivative operator, and we can, as with any derivative operator, express it as a coordinate derivative operator plus a vector field, one form of a certain kind, a Lie algebra valued one form. I mean, that feels a lot like a kind of Kretschmann style move. And so that suggests that, you know, what you're pointing to in that first step is a way of introducing, what you might call a kind of non-substantive general covariance. Oh, sorry, non-substantive gauge covariance by analogy to non-substantive general covariance. And then the sort of, what I think, I mean, it sounds like everyone agrees is the sort of physically substantive move is letting this derivative operator have non-trivial curvature, then giving it a dynamics that tells you what that non-trivial curvature is. And that's going to look a lot more like the introduction of substantive, or the need for substantive general covariance in one sense of that term, namely the observation that you can't work in coordinates if you want to allow for metrics of arbitrary curvature. So that's just again a way of kind of plugging it into these analogous debates in GR that might be interesting.
Mm-hmm. Yeah, that sounds right to me.
Oh, good.
All right, let's go back to Eric.
I think I actually have a short question. So you consider the inner product preserving maps. So these gauge, these local gauge transformations are inner product preserving maps, these point by point. But there's at least one inner product preserving map that you don't get in that way. That's just conjugation, and that since conjugation is not derivable from a local infinitesimal symmetry, I think actually it's not going to be a symmetry. It's not going to be a symmetry. When you add the exterior derivative of lambda term to make the Lagrangian invariant with regard to local gauge transformations, that no longer is invariant under conjugation, because minus exterior derivative of lambda is not going to be the same thing as minus exterior derivative of lambda conjugate.
Lambda is real.
Oh, you're right. Okay, I take it all back.
Good.
There, I told you the story.
Neil, is that your hand still up? Is that because you want another go? No.
No, sorry, that was just inattention.
Okay, are there any other questions? Comments, questions? Oh, Harvey, yep.
Well, could I just come back to something that that Eric raised at the very beginning about why we're looking at Lagrangians rather than field equations, for example, or the Lagrange equations, and understanding the symmetries. I mean, it's certainly true that certain systems, some special systems, can have inequivalent Lagrangians. But I think the important thing to remember is that there are symmetries of the field equations that are not necessarily symmetries of the Lagrangians. That's well known. But if all of the terms in the Lagrangian, if all the terms in the Lagrangian, all the fields are dynamical, then the symmetry of the quasi-symmetry of the Lagrangian will also be a symmetry of the field equations. So it doesn't really matter whether or not which Lagrangian you choose in the case of inequivalent Lagrangians, which is a rare case anyway. The fact is that if all the fields are dynamical, that's to say they satisfy Hamilton's principle, then the symmetries of the Lagrangian will coincide with the symmetries of the field equations. Does that assuage your doubts, Eric?
In part, but I guess a priori, I see no reason why we should exclude what you're calling special Lagrangians. Well, they're special only because they have this feature. I don't see why we should rule them out a priori on that ground alone. But it is true that so far as I know, well, no, that's actually not true. The free particle Lagrangian actually has these two inequivalent formulations. So that actually strikes me as a very physical Lagrangian. So I don't think that.
So, are you saying that if you choose one of these Lagrangians, and then you ask yourself, why are you considering the symmetry of the Lagrangian and not the symmetry of the equations of the field equation, the equations of motion? Wasn't that your point? What difference does it make if the equations of motion have inequivalent Lagrangians? I don't see what difference it makes.
Well, if the issue is that we're going to look for mappings that preserve something in order to try and figure out what structures we really need to a la Weil-Stein, then it depends on what structure you're looking to preserve. What class of mappings you choose depend on what structures you want to preserve. And if the class of mappings are different, depending on whether you want to preserve the Lagrangian or depending on whether you want to preserve the solutions, then at least prima facie, it's possible that you're going to end up giving different answers to what structure do I need to formulate the physics. Is it the structure I need to formulate to keep the Lagrangian invariant, or is it the structure I need to keep the solutions invariant? And those might end up being different.
I take your point.
All right. Are there any other questions or comments?
I'll just say I didn't see Eric's comments in the chat, which are wonderful. So I think Eric here is asking so this approach may not explain why there's a spin one field, but this trick does work over and over again, and that calls out for some kind of explanation. Yeah, I guess my answer to that is I guess along the lines of what I said before, which is if you posit, you know, as you're listing possible fields that you can have, you could list spin 0, spin half, you could add in a massless spin 1, or a system of mutually interacting massless spin 1s. And if you now just ask, what are the self-consistent ways that these fields can interact with each other with other fields? There are other self-consistency arguments that force this kind of local looking gauge invariance on you. You can't write down, for example, a system of mutually interacting massless spin 1s that don't look something like a non-abelian gauge theory. So I would just argue that there is another sort of explanation, but by Neil, you know, and that this is a good shortcut to guessing what those things have to look like first quantization. Canonical quantization is a shortcut. But again, the fact that it doesn't always work and that we don't always need to apply it. I think another example I would just give is, you know, it's often very convenient when looking at, you know, if I have, for example, a totally generic classical mechanical system that I'm describing in a Lagrangian formulation, for various reasons, it can be very convenient to write it in a reparameterization invariant form. And when you do this, you get a gauge invariance, reparameterization invariance. And, you know, if you do this for, you know, 4-dimensional fields, that gauge invariance is diffeomorphism invariance. And if you wanted, you would now have, the soil is sort of soft for putting dynamical gravitational fields into the picture. But we don't have to do that. And in fact, generically, we don't want to do that. The gauge invariance is mathematically convenient, but it doesn't compel us to reify anything or make anything physical. I still feel like that reification step is still a gap. But anyway.
All right. Well, Jim, do you want to say something, or Eric? No?
Yeah, I mean, I'm thinking about this. I don't think that I have any reaction immediately. I mean, the only thing I'm thinking about is, you know, Harvey's comments about having all of your fields be dynamical and applying Hamilton's principle uniformly is another kind of, in some ways, heuristic, but one that cuts against the idea that, well, you know, we can just put these fields in and maybe they're going to turn out to be dynamical and maybe they're not. And, you know, maybe it'll turn out that Hamilton's principle doesn't apply to all of the fields that exist in nature. There's a question of where to put our bets. But I don't know that there's anything to say beyond. We can invoke heuristics that have worked in the past, and we can observe that there have been cases where we haven't needed to invoke those heuristics and things seem to turn out okay. And now we're left in a place, well, you know, where are things going to end up 100 years from now? I'm not sure that much to say on that topic.
All right. Well, this has been a lovely 2-session chapter of the seminar for this semester. Jim, thank you very much for 2 beautiful talks and for wonderful discussions. You managed your time exceedingly well, and we just had so much time for questions and discussions, and that's really something that's very well executed. So thank you very much, Jim.
Thanks.
Thank you, Jim. It was really wonderful.
See you all soon, I hope.
We'll see you all next week.
And Jim.
Bye-bye, everyone.
Bye-bye.